Today, I will take you to explore the black hole. At the edge of a black hole, if you look back, you will see 100 versions of yourself. This is not magic. It refers to the photon sphere. After 15 seconds, not even light can escape your sight. Today, let's discuss a heavy topic. What would happen if you were thrown into a black hole? This time it's not science fiction. It is truly based on hardcore physics speculation. Before throwing you in, let's briefly review what a black hole is. Even the physicist Einstein once described a black hole as a place where God divided by zero. He didn't believe at all that such a thing could really exist in our universe. But look, humanity really found it. When those particularly massive and dense stars reach the end of their life, they undergo a transformation. They collapse in on themselves. There's nothing left. What they create is called the starting point, a mysterious point in space-time. It is said to have infinite density. Therefore, it has infinite gravity. General relativity gave us a revolutionary idea. Gravity is not a force acting on objects. It is merely space-time itself, the result of curvature caused by an object's mass. It completely explains how our Earth orbits the Sun, and how various planets rotate around their own homes. There is no solid surface inside a black hole. The singularity hidden inside is just too dense, causing a severe distortion of space-time, forming a well with vertical walls. In 1939, Albert Einstein himself even published a paper specifically stating that stars collapsing into singularities is unlikely. It will not happen in our universe. Coincidentally, in the same year, J. Robert Oppenheimer, that famous Oppenheimer, along with physicist Hartland Snyder, co-published a paper, Prediction: Stars can indeed collapse under their own gravity, collapse into a black hole. Let's talk about it again. What would happen if you were thrown into a black hole? This thing called a black hole. The most amazing thing is that anything can become one. Whether you're a star or a planet, or even a little person like us. As long as you are compressed to a size within the Schwarzschild radius, you can become a black hole. The German physicist Karl Schwarzschild was the first to discover an exact solution to Einstein's field equations. This discovery is both simple and beautiful. Take our Sun as an example. If all of its mass were compressed into a sphere with a radius of just 3 kilometers, hey, it would become a black hole. What about the Earth? It would become a sphere with a radius of about 9 millimeters. That's roughly the size of a marble. If we humans wanted to become black holes, that would be disastrous. We would have to be compressed to much smaller than a proton. Incredibly small. However, if we could really become that small, then we would also become a black hole. So which black hole should we throw you into? I think it's time to throw you into a black hole. But which one should we choose? We could choose a smaller one, but that would be so boring. Let's pick a bigger one instead. Some black holes' event horizons are larger than our entire solar system. That would require billions of solar masses. But that's just too exaggerated. How about we choose one that's closer to home? Sagittarius A*, the supermassive black hole located at the center of our galaxy. Aster, you are currently orbiting it. It is one of the only two black holes photographed by us. Now let's set the scene. Let's assume you and I fly there. We park the spaceship 1 trillion meters away from the event horizon. We are going to send you to the black hole. When you are in free fall, I will stay on the spaceship to observe. But this is the key. General relativity tells us, those who are near the black hole, the time you experience may be completely different from others. Because the black hole distorts space-time too severely. This effect was demonstrated in Interstellar. To record time, we'll give you a special watch. It will show from your perspective, and from my perspective on the spaceship, how much time has passed for each of us. Once we synchronize the watch, you can begin your journey into the black hole. When your journey begins, you will see the distant black hole rapidly consuming matter. That scene is incredible. Matter is heated to extremely high temperatures due to friction. If you were to take this scene and simulate it on a regular laptop, it would take over a decade. In reality, that disk would be a bright blue or even white. But in this simulation, it is rendered as orange. This makes it easier for us to observe. It's only been 30 minutes since you first checked your watch, and you've only completed 0.1% of the journey to the event horizon. So far, I only gained 11 more seconds than you on the spaceship. This time difference isn't too outrageous. Now we're closer to the black hole. The space-time around the black hole is creating all sorts of strange visual effects. Light emitted from the sides and even behind the black hole is being bent before it reaches your eyes. Let's take another look at the time. You've been gone for 2 hours, completing 1.4% of the journey, and I'm now ahead of you by 44 seconds on the ship. This time difference is a bit concerning, but it's not too absurd yet. The shadow of the black hole, the dark area in the middle, seems to be growing faster than we expected. This is all due to the gravitational lensing effect, which bends light that would otherwise pass by you onto your retina. A long time has passed. You finally check your watch again. This glance is startling. From your perspective, you left about 12 hours ago. But to me, on the spacecraft, I have been observing you, drifting toward the black hole for almost 15.5 hours. We are now very close to the black hole. Things are about to get very strange. Before you reach the point of no return, you will arrive at a strange and wondrous place. If you are frozen in this special place, in time, and then look around, that sight is sure to astonish you. You have reached the photon sphere. This is one of the strangest places in our known universe. One of the strangest places. In the region of the photon sphere, gravity is perfectly balanced, allowing photons to orbit the black hole. It is not matter emitting or reflecting light, but rather photons trapped in orbit. If this beam of light moves tangentially to the black hole, it can orbit. But if the path changes even slightly, photons will either fall into the black hole, or be sent off into space. Under these specific conditions, if you simply freeze at the photon sphere, and look around in all directions, you will see a mirrored image of yourself facing away from you. You would see multiple copies of the back of your head, staring into space. You are actually looking at yourself, as if you are standing next to yourself. No real-time technology is required. It's all due to the distortions of space-time itself. As you continue your journey, you are getting very close to the event horizon. Now we have passed the photon sphere. The black hole is occupying more and more of your field of vision. It feels like you are being swallowed by darkness. This is because the darkness is distorting around you. The 4 black facets reveal the back and sides of the shadow, along with what is present in flat space-time. The part that is usually visible to you has become empty space. You have been gone for 13 hours. In another 24 minutes, you will cross the event horizon. But from the spaceship, I have been observing your journey for nearly 20 hours. Another 18 minutes have passed. You check your watch again. Now I have been observing you for almost 40 hours. It's a good play for you. The last 18 minutes. For me, it lasted a full 18 hours. The final moment has arrived. In another 6 minutes, you will cross the black hole's event horizon. You close your eyes. Take a deep breath. Check your watch. But it seems to be broken. It shows. I have been watching you fall for an infinite amount of time. But it isn't broken at all. That's just how physics works. I spent decades on the spaceship, watching you slowly approach the event horizon. Eventually, I saw you redshift. This means I have to use an infrared telescope to see you. I will never be able to see you cross the event horizon, even if I could live forever. For you, the last 6 minutes for me lasted an eternity on the ship. This sounds like science fiction, like a daydream. But it's absolutely true. It jumps straight out of Einstein's equations. Now you are inside the event horizon. So what happens inside a black hole? Strangely, it's hard for you to notice. When you cross the event horizon, you can still look out at the universe, seeing distant stars, even seeing our ship floating in space. But all that light, like you, must rush towards the starting point. You've already passed the point of no return, that point of infinite density. Our laws of physics have all broken down. Time has stopped. If you want to escape the pull of the starting point, you must go faster than the speed of light. We all know that's impossible. A common misconception is that, if you look out at the universe, the intense time dilation effect will allow you to see the entire future of the universe. History unfolds before your eyes. But this is not really true, because it's like this thing again. As you approach the starting point, you will see the external universe compress into a thin little ring. Finally, when you are close enough to the starting point, your feet will be stretched out in front of you. Your body will be in the process of spaghettification. Stretch out, merging with the black hole, drifting together in the universe. Until eternity. Just thinking about this entire process gives one chills. Yet one can't help but want to explore it further. Black holes, these mysterious celestial bodies, truly make us feel both love and fear. General relativity hides counterintuitive inferences. The mathematical solution shows the black hole core may contain a space-time anomaly zone. Today, I want to tell you, throwing you into a black hole is absolutely not to harm you. When you touch the black hole singularity, perhaps you can explore the eruption of white holes,
experience wormhole teleportation, and then visit parallel universes.
These things sound like they belong in a fantasy novel, but they are all hidden in Einstein's equations. Are you ready to overturn your worldview? Fasten your seatbelts, we're about to speed off. You're already familiar with black holes. If black holes are like crazy vacuuming toilets, then white holes are like high-pressure water guns. This thing can be considered the twin brother of a black hole. They share the same face in mathematical formulas. But what they do is completely opposite. They only spit out, not consume. Not even light can hope to get in. Even more ridiculous is that there may be a wormhole connecting black holes and white holes. It's just like a universe-sized soda straw. But don't get too excited yet. White holes haven't been discovered by humans yet. Why is that? To put it metaphorically, a black hole is like a garbage can, solidly placed there. Whatever you throw in can only go in, not out. A white hole is like a treasure bag, anything can be poured out of it. But the cosmic factory has long stopped production. However, there's a recent explosive theory. When a black hole undergoes Hawking radiation evaporation, it may resurrect into a white hole. If this is true, our universe is very likely an infinite nesting doll. The current universe. Perhaps it was exploded out from a black hole turning into a white hole from the previous universe. Under certain circumstances, black holes and white holes can be connected through a completely different type of space-time, wormholes. Wormholes serve as an intermediary between parallel universes. You can imagine the taste of soup and whatever else. Hey, got it? But if you want to travel through space via wormholes, I can't blame you either. After all, it's theoretically possible. It's just that there is no evidence showing that white holes or wormholes actually exist in our universe. But you don't need to be pessimistic. Think about 100 years ago. Black holes were merely theoretical existences, weren't they? Here's the key point. What exactly are these other types of holes in space-time? Why do scientists and mathematicians calculate so many of these things? If they are real, what would they look like? I am our space. Today, I will take you on an exploration. Different types of space-time created by extreme curvature. I hope you won't end up with a mind as twisted as these warped space-time structures. Before we delve into the space-time physics described by old man Einstein's general relativity, regarding the space-time physics, I would like to start with a simple analogy. If I ask you to imagine a cone, you might think of one that points upwards, like a traffic cone, or one that points downwards, like an ice cream cone. These are our understandings of cones in the real world. But if you write down the most general mathematical equation for a cone and try to sketch it, you will get a figure that looks like two cones glued together. You see, the mathematical cone has two parts, one pointing upwards and one pointing downwards. They are connected at the tip, and what we perceive as a cone in the real world. In reality, it is just a truncated part of a complete mathematical cone. Black holes are the same. This structure is represented by physicists using Penrose diagrams. It packs infinite space-time into a finite diagram. A key feature of the Penrose diagram is that light propagates upward at a 45 degrees angle. This makes it easy to distinguish between areas where light can enter and areas where it cannot. In this diagram, Area 1 is the universe we are familiar with. Everything is available, from the past to the present, even the future. Region 2 is the black hole, isolated by the event horizon. Light can easily enter, but it's difficult to get out, no second chance. It is fundamentally impossible to escape. In the end, everything must crash into the singularity. Is ordinary matter the same? It can only move upward at a steeper angle. The power of this diagram lies in that it takes into account the situation when the black hole forms. Just like a star collapsing in on itself, when there was no event horizon in the past, light could travel freely. But this diagram is just a part of the mathematical description of black holes in general relativity. like a lonely ice cream cone. Now, let's imagine an ideal black hole. It has an infinite past, setting aside the troubles of collapsing stars. Next, you're going to have long hair. Region 1 still represents our conventional universe. Square root region 2 is still a black hole. Its future has an inevitable singularity. But mathematics also describes something that looks like the opposite of a black hole in region 3. Rather than saying it has a singularity in the future, it's more accurate to say it has a singularity in the past. If you plot the trajectory of light at a 45 degrees angle, you'll find that light can easily leave region 3, but it can never enter. This type of region is what we call a white hole. It is a traffic cone in spacetime. But this is not everything. If you look outside the white hole, you will find a section of spacetime marked as Zone 4. The connection it has with the black hole and white hole in the middle is the same as the connection in the regular universe. This section is a parallel universe. It is completely isolated from the universe in region 1, because even light cannot propagate from one region to another. The implication of all this is, the same mathematical equations that describe the conventional universe and black holes also describe parallel universes and white holes. This does not mean that every black hole comes with a white hole. Just like a cone, the real universe can contain a truncated part of a complete mathematical solution. But this really means that, even if white holes are rarer than their black hole counterparts, or even if there are no connections to white holes in our universe, this does not make them any less real in a scientific sense, because they are equally consistent with the laws of physics. I promised before to let you teleport through a wormhole, to attempt to connect to parallel universes. So buckle up, because you are about to enter a whole new layer of spacetime distortion. Before going in, you should know about the no-air theorem. Black holes have at most 3 properties: mass, charge, and spin. The Penrose diagram I just mentioned only describes the simplest black holes. Charged or rotating black holes are more complex. And also more interesting, it changes our understanding of singularities. It also brings about a new spacetime region. Take the Penrose diagram of a rotating black hole as an example. There are now 8 regions, in infinite repetition. Regions 1 to 4 are still the regular universe, black holes, white holes, and parallel universes. But in a rotating black hole, its structure no longer has an unavoidable singularity. The same applies to white holes. After crossing the event horizon of a rotating black hole, you will be pulled towards the center. Then you will cross into the inner horizon, where spacetime is no longer distorted. You can float freely, even touch the singularity of the universe. Here, you are in the wormhole. If you are not isolated from the outside world, this is a great opportunity to show off. You can choose to bypass the singularity and go to region 6 or 8. But this could be a flaw of general relativity, because it may lead to causal paradoxes. It's safer to move outward, crossing the inner horizon, enter the white hole, and then into a brand new universe. But your friends and family may not be there waiting for you. Your old universe has experienced infinite time. Back to reality, traveling through wormholes is interesting. But you might not survive, and the wormhole could collapse. There are many rotating black holes in the universe, but the internal conditions are unknown. There are 2 main reasons. One is that the assumptions during black hole formation are violated. The second is that general relativity might only be approximately correct. It may fail near the singularity. Therefore, some predictions of the Penrose diagram may be inaccurate. However, the existence of white holes is still possible. This leaves us room for imagination. Recently, there was a hypothesis that a white hole may be born when a black hole dies. This is not witchcraft. Rather, it is a scientific understanding of the black hole life cycle. There is mathematical support for it. Black holes emit Hawking radiation and gradually shrink. When they reach Planck mass, quantum gravity theory predicts it may become a white hole, ejecting contents back into the universe. Although white holes are small, they can contain immense entropy. May solve the information paradox. As the white hole releases information, it slowly disappears. The curvature of spacetime disappears, and the life cycle ends. Finally, I'll leave you all with something to think about. General relativity predicts that the universe once had a singularity, just like a white hole. If a white hole can be born at the moment a black hole collapses, then, could our universe also have originated from an even older spacetime? It sounds crazy. But look, quantum gravity theory says this might be the truth. Science begins with curiosity about the unknown. There is still a long way to go in exploring the universe. Give me a follow back. Can you believe it? Scientists have analyzed the data from the Webb telescope and found that we might be living inside a black hole of a larger universe. These findings not only challenge the scientific textbooks, but also prompt a re-evaluation of Einstein's theories. From the origin of the universe inside a black hole, to the mirror particles behind dark matter, and next, we'll take you through the ultimate puzzles that overturn human understanding. Since the launch of the James Webb Space Telescope, it has observed those mature primordial galaxies, which, in the context of the universe at that time, appear to be very old, large, and well-structured, completely mismatched with what galaxies should look like during that period. It's like being in a kindergarten, and suddenly seeing a group of college students in class. Isn't that perplexing? So their existence directly challenges the existing theories of cosmic evolution. However, is it possible that the issue does not lie with the model itself, but rather, we are standing in the wrong position? For example, what if we try a different cosmic perspective? What if the James Webb Telescope is actually guiding us to understand a completely new reality? This crucial aspect has to be explained by redshift. Redshift is the stretching of light due to the expansion of the universe. The farther away a galaxy is, the more its light is stretched. Astronomers use this to measure how far away galaxies are and how old they are. This time, the James Webb Space Telescope is really giving it its all. It's almost seen the universe as it was 13.5 billion years ago. At that time, the universe was just 13.8 billion years old. According to the standard model, galaxies at this stage should be small and irregularly shaped. But what the James Webb Telescope has observed are all large and regular galaxies, all at once. Scientists can't sit still anymore. They are rethinking their understanding of the universe. Even more outrageous things are yet to come. After the James Webb Space Telescope's Advanced Deep Field Survey observed 263 galaxies, it found their motion remarkably coordinated. This suggests that our universe might be residing inside some black hole. A new study analyzing the James Webb Space Telescope observations of the early universe reveal a strange fact. Most galaxies are rotating in the same direction. The lines formed by the curved tips of those galaxies' spiral arms help us identify their direction of rotation. According to logic, if the universe were truly random, the rotation directions of galaxies should be evenly split between two directions. However, the situation discovered by the researchers does not align at all with existing cosmological models. It might just be suggesting our universe might actually be inside a black hole. We need to figure this out. We first need to take a look at what a black hole is. When matter collapses under the force of gravity to form a black hole, it creates an event horizon. It's a boundary, and once you cross it, nothing can escape, not even light. For an outside observer, an object that crosses this boundary is completely finished. But what lies inside the event horizon is anyone's guess. At this moment, black hole cosmology, also known as Schwarzschild cosmology, it was time for it to take the stage. It says that the universe we can see might just be the inside of a black hole in a larger universe. This brings us back to the time of the Big Bang. The standard model states that the universe began from a singularity of infinite density, just like the center of a black hole. If our universe is really a black hole in a larger universe, then the Big Bang was not an expansion of matter into empty space, but rather a collapse of matter into a black hole, which then creates a new universe inside. In this way, every black hole in our universe could be a gateway to a new universe. This could also explain why the fundamental constants of our universe seem finely tuned, suitable for life to exist. Because black holes that can create stable universes could allow for long-lasting existence, and then give rise to new universes. Scientists are pondering that this theory might unlock many mysteries of the universe. For example, black holes have a particularly high entropy, which corresponds to the immense amount of information in our universe. For example, in the extended theories of general relativity, such as the Einstein-Cartan gravity theory, I mentioned the twisting of space-time. Twisting takes into account the effect of particle spin on space-time curvature. Some theories suggest that, at particularly high densities, this kind of space-time distortion can generate repulsive forces. In simple terms, it prevents the emergence of singularities. If that's the case, black holes could undergo a big bounce. The core rebounds and then expands outward. It might even create a new universe. Scientists also say that, if there is a rapid rebound after the big bounce, that could mark the beginning of our universe's expansion. In other words, the Big Bang. Therefore, this is not a singularity exploding out of nowhere, but rather reborn from the core of a black hole in a larger universe. If this theory holds water, it would fundamentally overturn our understanding of the origin of the universe. The cycle of the universe would become a continuous, self-replicating process. Additionally, the universe might have a preferred axis. When observing the large-scale structure of the universe, it has been found that the distribution and motion of galaxies seem to be somewhat aligned. It's not completely random. This so-called cosmic anisotropy challenges the widely accepted cosmological principles. That is, the universe should be isotropic and homogeneous on large scales. If the universe truly has a preferred direction, it may suggest that there are unknown physical laws at play. It could be related to how our universe formed within black holes, or it could be connected to the interactions of fundamental forces on large scales. However, the matter of primordial massive galaxies has also raised questions about the evolution of the universe. But we should also be cautious. Perhaps there are more ordinary explanations. Maybe some previous measurements of our universe were incorrect. For example, the rotation speed of the Milky Way, or the universe might be older than we think. Regardless, the universe is turning out to be even more mysterious than we once thought. The fact that galaxies don't rotate uniformly, this is likely to prompt astrophysicists to re-examine their understanding of the universe. Do you think our universe is inside a black hole? Although this idea is quite appealing, a recent research paper suggests that there is a mirror universe. Time runs backward in there. Have you heard of Occam's razor? In scientific reasoning, this is a very useful principle. To give an example, if astronomers see unexplained light on other planets, if they directly say that it's aliens, that would be too hasty. Occam's razor reminds us to first consider simple explanations, such as atmospheric conditions or natural phenomena of the planet itself. So why mention the Occam's razor here? Because many inflation models suggest that the rapid expansion of the universe in its early stages would generate long-wavelength gravitational waves. These are ripples in space-time. If we could detect these waves, it would add significant weight to inflation theory. Scientists have indeed detected gravitational waves now, but those are all from events like black hole mergers or neutron-star collisions. Even though we've gone through a heck of a lot to search for it, but we just can't find any trace of primordial gravitational waves. Each new experiment rules out more inflation models. While inflation theory does explain why the universe appears so homogeneous on large scales, it also brings about several new problems. For example, what kind of energy field is driving the expansion? Does inflation require the universe to have very specific initial conditions at the start? But why do these conditions arise? No one can say for sure. Some inflation models even suggest an infinite bubble universe. This leads to a host of philosophical and scientific questions about whether they can be tested, and the nature of physical reality. So, if we set aside the Occam's razor factor, it means assuming there is no simpler explanation. This matter falls on Neil Turok, the chair of theoretical physics at Higgs, and his colleague Latham Boyle. They developed a new theoretical model, trying to do this without relying on traditional inflation theory or string theory, to solve fundamental cosmological problems. If we use Einstein's general relativity and known physical laws to reverse the time of the universe, it ultimately shrinks to a point, the initial singularity. To understand the universe's dense and hot state at the beginning of the Big Bang, theorists like Nobel laureate Roger Penrose found that there is a key symmetry in the laws of light and massless particles, called conformal symmetry. What this thing means is, light and massless particles are not squeezed like other matter during the Big Bang. They can pass directly through those extreme environments. You can imagine the universe as a piece of elastic rubber. There is a picture on it. If you stretch or squeeze this rubber, the size of the picture will change, but the shape will remain the same. Conformal symmetry means that, regardless of how the universe scales, its structure remains unchanged. This might mean that the uniformity of the universe naturally emerges from this symmetry, rather than being shaped by an explosive event like expansion. They propose that the initial singularity is not a one-way starting point, but like a mirror in time, One side moves forward in time, while the other side moves backward in time. It's like the universe is looking in a mirror. The Big Bang acts as a mirror to every physical process. It reflects space-time and particles in reverse. This follows CPT symmetry. It represents a fundamental balance in nature. You can imagine the universe as a grand stage. Particles are performing a play. In this play, there are three rules: charge, parity, and time. Charge is like swapping matter and antimatter. Parity is like flipping the scene in a mirror. Time is like playing the play in reverse. If you reverse all three at the same time, the laws of physics remain unchanged. The universe continues to operate as usual. It's like a well-rehearsed performance. No matter how you twist things, there won't be any mishaps. However, in our universe, there are more particles than antiparticles. Time also only moves in one direction. This seems to break CPT symmetry. The idea of a mirror universe comes to restore this symmetry. It is said that our universe has a mirror counterpart. In there, time flows backward, and antiparticles have the upper hand. This parallel universe may not necessarily be a real place. It might just be a mathematical tool, used to explain the symmetry during the origin of the universe. Their theory also involves dark matter. Neutrinos are a type of light particle. They travel at speeds close to the speed of light. The spin direction is left-hand. However, it is predicted that stable heavy right-handed neutrinos could be candidates for dark matter, because they are only affected by gravity. Turok and Boyle calculated using the mirror hypothesis that these right-handed neutrinos could indeed explain dark matter K. This theory also states that if dark matter is composed of heavy right-handed neutrinos, then among the three known light neutrinos, at least one must have a mass of 0. This prediction is being validated through the study of how galaxies and other cosmic structures are laid out in space, observing how matter accumulates in the universe. This might lead to clues about neutrino mass. Thus, we can assess the reliability of this dark matter theory. Scientists have also investigated why the universe appears flat and uniform on a large scale. They use entropy to explain this. Entropy describes the likelihood of a certain configuration. They discovered that a flat and rapidly expanding universe, with a slight positive acceleration, is the most likely state to occur. Additionally, they pointed out that the density variations usually thought to be related to expansion can actually be explained using quantum fields. However, this new theory still needs to undergo more tests to establish itself scientifically. Turok wrote in the Physical Review letters when publishing the team's findings to view the Big Bang as a mirror, which can effectively explain the features of the universe that seem to conflict with physical laws. But Turok also noted that, even if proven wrong, it reminds us that there may be a simpler explanation than the standard model. What does everyone think about this? Let me know in the comments. Thank you for watching the video until the end. Leave a comment about the topic you want us to create. Don't forget to like and subscribe so you don't miss any videos.